Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Dr. Adam Klett.
Thank you, William, and hello to everybody. Thanks for tuning in today. On today's Tech to Tech episode, we're going to be talking about analytical techniques that many of us within the electronics manufacturing industry rely heavily on, but around which many misconceptions are held. Whether you yourself carry out these tests, or if you have them sent to an outside lab and you just receive the results back, it's important to have at least an introductory understanding of what was done to make sure that the conclusions that you draw from the data are correct. So here's a quick outline of the techniques that we're going to be discussing today and the talking points for each. We're going to review ion chromatography, or IC, resistivity of solvent extract, commonly known as ROSE, and surface insulation resistance, or SIR. For each of these analytical techniques, we're going to discuss what is actually being measured. We're going to give a brief description about how the instrument works. We're going to talk about what information you can gain from it. And then most importantly, we're going to be talking about what the limitations are. So first, let's start with ion chromatography, or IC. Now, chromatography in general is a method for separating things, right? There are many different types of chromatography depending on the specifics of the system. For example, you can have gas chromatography, or GC, which is used to separate mixtures of gases, or liquid chromatography, which can be used to separate things, you can probably guess, dissolved in a liquid. In the case of ion chromatography, though, we're going to be separating ions that are dissolved in an extract solution. Now, the reason we want to separate them is because it makes it much easier to not only identify them, but also quantify them. A classic example of this is to separate the pigments that make up an ink. It's very hard to look at an ink and know which specific components and how much of each are present. But if you can somehow separate them, it makes it a lot easier to identify them and measure how much of each you have. So during an IC experiment, what you're measuring is the elution time, or the time it takes for an ion to separate from the mixture. You get a curve like the one shown on the slide on the left. Each peak is a different ion, and the size of the peak is related to how much of that ion is present. This can then be converted into the table like the one you see on your right. So how does an IC system even work? Well, first, a sample board is placed into a clean bag with an extraction solvent. Most of the times it's IPA and water, to allow those ions present on the board to dissolve. That solvent is then injected into the IC system. As the sample makes its way through the column, the ions are going to separate. The ions that have stronger chemical interactions with that column will take a lot longer, and the ions that have weaker interactions will elute much quicker. As the ions exit the column, they're then detected, most systems, using a conductivity detector. So what information can we gain from this test? Well, this test will quantify the amount of ionic contamination present on the surface of a circuit board, which can indicate the level of cleanliness. This method is usually used for process qualification or failure analysis, as it can take many hours to complete a single test. Now, since this method relies on measuring elution times, the identity of those ions can't be guaranteed without another method of detection, like mass spectroscopy. There are many components that can elute at similar times, so knowing the identity of a peak can be problematic in complicated mixtures. Also, some of the instruments, since the instrument is calibrated with known standards, samples must be within this calibration range. If not, the samples will need to either be concentrated or diluted to get data that can be trusted. Lastly, this measurement is an overall measurement across the entire surface area of the board. It cannot detect local areas of high contamination, which could lead to a false sense of cleanliness. All right, so now I'd like to move on to ROSE. So ROSE, or resistivity of solvent extract, measures the conductivity of an extract solvent similar to IC. However, in this case, we're not pre-separating the ions. We're going to be measuring the bulk conductivity of the mixture. And this can be used to estimate the amount of ionic residues present on the substrate. So how does it work? Well, it's a pretty simple measurement that involves submerging a sample into a solvent bath and then measuring the change in conductivity. As more residues dissolve into the solvent, the higher the measured conductivity will be, as seen in your figure on the right. So what can be gained from this method? Well, it can be used to estimate the amount of ionic residues on the surface of a circuit board. This method is generally used as a process control tool because it takes only a few minutes. However, there are some limitations. First, since we're not separating the ions like an IC, we cannot quantify them because different ions change their conductivity differently. What we report is sodium chloride equivalence, which is not the amount of sodium chloride, but it's the amount of sodium chloride which would have to have been on the board to have the same effect on the change in conductivity. Also, as with IC, this method can only detect the soluble residues on the surface and is only an average measurement across the surface area of the entire board. So again, we won't be able to detect small areas of high concentration. All right, so now I'd like to move on to surface insulation resistance, or SIR. Now, during an SIR measurement, the electrical resistance across two pads on a circuit board is measured. That's it. We know that the presence of ionic contamination on the surface will drop the measured resistance. So the higher the measured value of resistance we get, the cleaner the board is. So how does it work? Well, a coupon, like the one shown in the figure, is placed in an environmental chamber at an elevated temperature and relative humidity. For example, 40 degrees C and 90% relative humidity. Then we apply a voltage across the pattern. For example, 5 volts is common. And then we just measure the resistance continuously for up to 7 days. So what information can we get from this method? Well, this can be a quantitative method to assess the level of cleanliness of a circuit board. It's called out in IPC standards as a method for gathering the objective evidence that we need to qualify a cleaning process. Now, since this method takes 7 days, it's generally not used as a process control tool. So what are the limitations of this method? Well, first, the test is carried out on a test coupon and not on production hardware. However, the test coupons can be designed to be representative of your own production hardware. Also, the IPC test methods don't provide much guidance for testing at high voltages. There's a few caveats that you need to be considered before running those tests. And lastly, a full test takes up to 7 days to complete, which limits this to process qualification efforts. All right, so now I'd like to get into some frequently asked questions. First, if I see a spike in an ion in an IC report, how can I figure out the source? Well, this can be a tough problem to solve, especially if the problem appears to be random or arises with no apparent cause. The best way, though, to detect the source of ionic contamination is to walk your production line, starting in your receiving department and looking at every step along the way. If a process has changed, this is a great place to start. Also, keep in mind that contamination can come from anywhere, including the bare boards or components, and to anything including human contamination as well, like sweat, fingerprints, and so forth. All right, the second question that I frequently get asked is, what's the maximum allowed ROSE measurement to still be considered clean? Well, the IPC recently changed their stance on this, and there is no longer a universal number to indicate clean. Your boards must be shown to be clean using a different technique, like SIR, and then correlated back to the ROSE data. A process that has been qualified can be monitored using SPC techniques and the upper and lower limits will be defined during that process. All right, and the last question that we have is, why do some SIR patterns look so noisy and others look very flat? Well, there are a few sources of noisy SIR data. The first and most important reason, though, is that your board's dirty. Many times, sporadic and noisy data can be attributed to contamination on the board. However, if that's not the case and you've already ruled that out, there could be an issue with the experimental setup. For example, condensation dripping onto the test coupons from inside of the test chamber can cause spikes in the data. All right, now with that, I'd like to thank you for your attention, and now I'll turn it back over to you, William. Thanks.
Thanks, Adam. Thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@kyzen.com, and we will have someone follow up with you as soon as possible. If you like this video, be sure to follow us on our social media platforms for more expert cleaning content.